Okay, so we're going to start out today by taking a look at functional groups in organic chemistry. This is the quiz that you're going to have on Thursday, or something similar to it. So take a look at the blank spaces, take a moment, and draw the structures for the compounds where the structures are absent. And if you need to, press pause so that you have enough time to complete the exercise. Go ahead and check your work. One of the things that we're looking for here is an example is fine. So if you want to put something in place of the R groups, those are just placeholders for any carbon, CH2, CH3 group. The goal is that by the time you are taking your exam on Tuesday, that you are familiar with the functional groups. So today we're going to be talking about combustion. And we're specifically going to be thinking about alkanes and alkenes and alkynes. So chemical compounds that only have carbons and hydrogens. This is a model of a propane combustion. So this would be something if you were grilling over the weekend, maybe use charcoal. But one of the other ways that folks prepare food is to use a propane gas grill. And so this would be the combustion reaction that takes place. Your propane is C3H8 with oxygen, and that produces carbon dioxide, water, and then heat and light. So if we think about combustion reactions, generally speaking, there's a couple of things we're going to notice. So for each carbon we add, so methane, propane, butane, we should be able to derive the generic combustion expression. So here we're going to balance the equation looking at the number of oxygen molecules that we're using, the number of carbon dioxide, and the number of water based on the number of carbons and hydrogens we have. So take a moment, write out the balanced equations for these three hydrocarbons. Now, the reason we lead off with combustion is because it's a common and accessible example. What we're looking at in terms of hydrocarbons are compounds that are only composed of carbon and hydrogen. Saturated hydrocarbon is going to be a hydrocarbon that has only carbon-carbon single bonds, whereas an alkane is a saturated hydrocarbon whose carbons are arranged in an open chain. We can also use the terminology an aliphatic hydrocarbon. That's an alternate name for the alkanes. If we take a look at each of these molecules, they're formed from a reaction between carbon, heteroatom, or hydrogen. And you'll notice that all of these are covalent bonds because they're shared electrons, but you'll also notice that there are a couple of patterns, and those patterns are single bonds, double bonds, and although we have not shown it, triple bonds. So take a moment, think about how you would draw the shorthand structures, or in this case, the starting materials and the products if they're missing. So take a moment and make sense of the valence electrons of carbon and the components that it can combine with. If we think about what we've covered so far, so in chapter 1 and 2, we were really looking at water and the interaction of acids and bases. For chapters 3 and 4 and 5 and a little bit of 9, we're going to be looking at alkanes, alkenes, alkynes, and arenes. So we're going to be looking at carbon-carbon bonding, or only carbon-carbon single bonds, or carbon-carbon double bonds, or carbon-carbon triple bonds, or some aromatic compounds like what we see here. So if we think about shape, each of these molecules is going to have some type of geometry. When we have single bonds, we know that it's going to be tetrahedral geometry, where all carbons are sp3 hybridized, and then all of our bond angles are going to be approximately 109.5. If we think about our line angle formula, this is an abbreviated way to draw out structural formulas, where each line represents a single bond, each line ending represents a CH3 group, and each vertex or angle represents a carbon atom. You'll notice that none of the hydrogens are drawn in. None of the carbons are drawn in. Those are implied or implicit. So here you have the ball and stick model. Here you have the line angle formula. You have the structural formula and then the names below. You're probably most familiar with drawing the structural formula, but from here on out, I want you to practice using the line angle formula. So when we think about converting from chemical formulas to line angle drawings, we have several examples. So I'd like you to go ahead and take each of these structural formulas and convert them to line angle drawings. And then once you have 6 line angle drawings for the molecules that are above, I'd like you to go ahead and choose one and rotate it 90 degrees and then draw it again. Choose another and flip it horizontally and draw it again. Choose one and rotate it 180 degrees and draw it again. Choose one, flip it vertically and draw it again, and then choose one and rotate it 270 degrees and draw it again. And the reason why we do this is because the gymnastics of molecules is pervasive. We tend to think of molecules as being static, but actually they're always moving. They're typically rotating, and particularly if they have single bonds, they're going to have rotation, which means that their structure, what it could look like, will vary. When we think about alkanes, one of the things we need to be able to do is recognize the prefix. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. And then the molecular formula that corresponds to that prefix, and then what that condensed structural formula would look like. You need to know all of the first 10 and be familiar with the structure of up through 20. So these are the prefixes. This is the number of carbon atoms. Probably the easiest way to review for this is to put it on flashcards. So take a moment, see if you can find the pattern. What are the exceptions to the pattern? Take a moment and investigate that. The pattern here, right, is that it's Cn, right, where N is the number of carbon atoms, and then either N, right, 2N plus 2, 2N, or 2N minus 2. That's going to determine whether it's an alkane, an alkene, or an alkyne. When we're thinking about constitutional isomers, these are compounds with the same molecular formula, but a different connectivity of their atoms. So what are 2 constitutional isomers with the molecular formula C4 and H10? Can you draw them? The reason why we're starting to think about constitutional isomers is because if we have only 1 carbon atom, then obviously there's no constitutional isomers. If we have 5 carbon atoms, we have 3. If we have 10, there are 75. And you can see quickly how the more carbons we have in our structure, the greater the potential there is for constitutional isomers. We're going to think about naming. So the parent name is the longest carbon chain. A substituent is any group that's bonded to the parent chain. So these are some common substituents: methyl, ethyl, propyl, isopropyl, butyl, isobutyl, sec-butyl, and tert-butyl. So notice here there are abbreviations that correspond to the position of the methyl with respect to the rest of the substituent. So we're going to take a moment and practice. Here's an example. So here's butane. We're going to remove the H from C1 and replace it with OH. That gives us 1-butanol, or N-butanol. If we were to put that hydroxide group, or OH, at the second position, that would be what's known as sec-butanol. So take a moment, and using this as the example, practice drawing 1-pentanol and sec-pentanol. Here's another example. This is isobutane. I want you to think about drawing isopropanol, and then I want you to think about why you cannot draw tert-propanol. And again, if you need a moment, just take a pause. When we're looking at alkanes and replacing, say for example, the hydrogens with an OH, or in this case with a chloride, we want to make sure that we pay attention to how we name those compounds. If it's a 1, it's 1-butyl or N-butyl chloride. If it's a 2, it's a sec-butyl. If it's essentially this T, then we can think of that as T-butyl. And if it's 1-chloro-2-methyl propane, then that would be isobutyl chloride. So there's 4 types of butyl groups that we would see when we're naming molecules, and this is the summary of those. So when we're thinking about naming alkanes, it's the name of an alkane with an unbranched chain that consists of a prefix and then the suffix ane. Ane refers to alkanes. So for branched alkanes, the parent chain is the longest chain of carbon atoms. Each substituent is then given a name and a number. If there is one substituent, we're going to number the chain from the end that gives it the lower number. If there are 2 or more identical substituents, we're going to number the parent chain from the end that gives the lower number to the substituent encountered first. The number of times that the substituent occurred or is encountered first, so the number of times the substituent occurs is indicated by the prefixes di, tri, tetra, and so on. So take a moment and see if you can name the following compound. So this would be 2,4-dimethylhexane as opposed to 3,5-dimethylhexane. If there are 2 or more different substituents, then we list them in alphabetical order, and we number from the end of the chain that gives the substituent encountered first the lower number. So take a moment and see if you can name this compound. So this would be 3-ethyl-5-methyl heptane. The prefixes di, tri, tetra are not included in alphabetization, so iso as an isopropyl would be included in alphabetization. So in the following example, when we're alphabetizing the names, that's going to be ethyl and methyl. We don't worry about the dimethyl. We exclude that from our alphabetizing. So take a moment and draw the following molecules: N-bromohexane, sec-bromohexane, isobromohexane, and tert-bromohexane, and then provide an alternate IUPAC name for each of these molecules. When we're thinking about alkanes, it's important that we understand whether they're primary, secondary, tertiary, or quaternary. So primary would be a carbon that's bonded to one other carbon. Secondary is a carbon bonded to 2 other carbons. Tertiary is a carbon bonded to 3 other carbons. And then quaternary is a carbon bonded to 4 other carbons. So take a moment and identify which of these carbons is primary, secondary, tertiary, or quaternary. So as you can see, how sterically hindered a compound depends largely upon whether or not it's quaternary. Tertiary is still fairly crowded, as we can see here, whereas primary and secondary are less crowded. So the general formula for alkanes is CnH2n. So 5- and 6-membered rings are the most common besides alkenes. So the structure and nomenclature of compounds that lose 2 hydrogens, right? If they're a ring form, it's the corresponding open chain alkane with cyclo, the name on each substituent on the ring. If there are 2 substituents, then we number the ring from the substituent of lower alphabetical order. And then if there are 3 or more substituents, we number the ring to give them the lowest possible set of numbers, and then we list them in alphabetical order. So take a moment. Here are 2 examples for you: isopropyl cyclopentane and 1-tert-butyl-4-methyl-cyclohexane. Using those as examples, can you think about how you would name each of these cycloalkanes? So 1-isobutyl, that's this component. 2-methyl, that's this component. 1-ethyl, 1-methyl cyclopropane. You can see here, right, we have to pay particular attention to the order and the numbering of each of the substituents. So if we think about alkanes, it's a prefix, infix, suffix, where the prefix tells the number of carbon atoms in the parent, the infix tells the nature of the carbon-carbon bond, and then the suffix is going to tell the class of compounds. So ane is all single bonds, ene is 1 or more double bonds, ine is 1 or more triple bonds, So keep in mind that the infix refers to the nature of the CC bonds in the parent chain. So think about the pattern. What is the difference between single, double, and triple bonds? It really comes down to how many hydrogens are found on those carbons. So if we think about our prefix, infix, and suffix, our suffix, like E, tells us hydrocarbon, ol tells us alcohol, al tells us aldehyde, on tells us ketone, and oic acid tells us carboxylic acid. So for example, let's break this down. Propene, so Propene, so that's 3 carbons, a double bond, and only carbons and hydrogens. Ethanol is 2 carbons, only single bonds, and there's an alcohol. Butanone, 4 carbons, single bonds, and a ketone, whereas butanal is 4 carbons, single bonds, and an aldehyde. Can you do the last 4? Draw the molecules and then provide an appropriate IUPAC name. Next time, we're going to be looking at alkenes and conformation. So thanks again for your time and attention. We'll see you in class.